right. I would say we get started. Hello, everybody. Welcome to our webinar. It's a pleasure to have you here on board with us. My name is Tobias Berg. I have the honor of being your facilitator and moderator today. I work in BASF as communication manager for our catalyst business. I'm located in BASF's headquarters in Ludwigshafen, Germany, and have the great honor to be your moderator and to be part of this fantastic BASF team. Before we actually jump into the topic, I would like to present a few housekeeping rules for our webinar today. Jochen, if you please go to the next one. It is really great to have you here on board. In order to have the best experience possible, I kindly ask you to keep your microphones muted and your cameras off. I think this functionality is disabled anyway. Whenever you want to reach out to us with questions, with remarks, you do find the Q&A function on top of your screen, and you can use that anytime. We do have a few breaks in between where we might ask your questions, or we have definitely time at the end of the webinar to answer the questions that you put into the Q&A function. If you would like to ask personally, you can also let us know, and we will make sure to unmute you, and you can also then vocalize your question if you want to. We will record the presentation and will share the video with you in the next upcoming days. So I think this is the most important part to begin with. What definitely is on top of the agenda is please enjoy the webinar. It's going to be an interesting one, so that is definitely something to look forward to. Before then, I would like to really present to you who is our expert today. Spotlight on Jochen. You can see Jochen here already in the screen. Jochen is our technology manager for sulfuric acid catalysts in BASF. He is also located in Germany. Jochen studied chemistry and holds a PhD with a focus on polymer chemistry. He joined BASF back in 2017 as a lab leader in research, and ever since 2022, he has been our technology manager for sulfuric acid catalysts for the EMEA region. And I'm also super happy to not only present Jochen, but also Saul. Although his picture is a bit blurry here, he is with us in high quality. Saul is our sales representative for Sub-Saharan Africa. He's located in South Africa. He also studied chemistry in South Africa and holds a PhD focused on the Sasol's Fischer-Tropsch synthesis technology. He joined BASF already in the year 2000 and is currently supports the business as sales and technology support for the Sub-Saharan Africa team. So super happy to have the two experts on board today who will present and also be able to ask questions. And then, before we then actually start, please allow me to do one announcement. Please go to the next one. We are super happy to be present at this year's Sulfur and Sulfuric Acid Conference at the end of May in Stellenbosch. We will be there to present on sulfuric acid SO2 emission limits and how to reduce them. So if you like the content of today's webinar, if you want to meet the team in person, please make sure to stop by. We will host a technical workshop and we will be exhibitor. So there is plenty of time and occasion to meet the team. We will be at exhibition stand number 1, so that's easy to remember. A very special thanks goes to SIME, the Southern African Institute of Mining and Metallurgy. They did not only, or will not only, organized the conference, but they also facilitated and supported strongly in today's webinar. So thank you so very much for your support. And now, without further ado, it's time to jump into the webinar, how to stay ahead of today's and future SO2 emission limits. Jochen, please take it away. Have fun.
Perfect. Thank you very much, Tobias, for the kind introduction, and also welcome to everyone joining today's webinar with the title Staying Ahead of Today's and Future SO2 Limitations and Why Superior Catalyst Shape and Composition is so important for that. I will start with a short historical overview of BASF in terms of sulfuric acid and sulfuric acid catalyst production, because we have a very long and deep knowledge and experience in sulfuric acid production, also with the catalyst. So since the founding of our company, BASF, in 1865, we already started up the first plant for sulfuric acid production 1 year later. And after that, we implemented in 1888 the contact process in our production. And all of the sulfuric acid was basically produced for captive use only for our own internal production needs. And since we needed more and more of sulfuric acid, we also started developing catalysts to produce sulfuric acid. And in 1913, BASF was granted the first patent on the technology based on vanadium pentoxide, potassium oxide, and a silicon carrier, which is basically a technology we're still using up to date. And with this technology, we were able to build a new plant and reach a production capacity of 120 kilotons per annum. Today, this sounds a bit small, but at the time, this was the biggest sulfuric acid production site in the world. And since this technology was so well received and also reliable, and we decided to also enter the market for sulfuric acid catalyst and sell the catalyst also to people producing sulfuric acid globally. And then there came a long time where we had like global development of the catalyst, and things were moving and increasing towards current needs. And in 2010, we actually decided to step up a bit and starting to work on our new generation technologies for sulfuric acid catalyst. So in 2010, we started to introduce our high performance catalyst, which was the cesium promoted 04116. And with that, we decided that we would need to step it up even further, and we were focusing more on geometry of catalysts, so new shape geometries. And with this, we launched in 2016 the first Quattro shape, which is the cesium promoted 04115 catalyst, which is the first member of our high performance catalyst family. Moving then on in 2020 to also release our vanadium based catalyst 04110 and 111. And in 2021, we finished our family of sulfuric acid catalyst compositions with the 116 Quattro, which we just launched in the starring shaped 11 years beforehand. And we did stop. So what we also did when we started working on geometries, we explored new technologies. And with this in 2022, we launched the first sulfuric acid catalyst, which was based on a technology using 3D printing, which we call X3D technology. And we're still not stopping, we're still developing and moving on. So this is basically more than 150 years of experience in sulfuric acid catalyst and sulfuric acid production, which will benefit you to increase your capacity and also reduce your emissions. Moving on, I already said we are like a global company for producing sulfuric acid. You can see here where we are active in terms of sulfuric acid production. So we have two sites, one in Germany, one in Shanghai, where we produce the catalyst for the sulfuric acid. And we have more than 13 sites, sulfonation sites or sulfuric acid sites producing sulfuric acid for captive use only all over the world. And since this is about new geometries, I will mainly focus here on Quattro catalysts, so our whole performance catalyst family. And basically the reasoning why we changed the shape from the starring, you might all know, to a new shape is that there's different things to influence activity and also performance of a catalyst. First thing, and this is the thing which is quite obvious if you compare this to like the old catalyst star shape, is that the shape. This is something which is quite obvious. If you change the shape, you will have a different performance of the catalyst. And the shape mostly influences the pressure drop and this geometric surface area. So this is something, if you change the shape, you always have an impact on your pressure drop in the plant and the surface area, which relates to the activity. Secondly, what you can do to influence the activity is to work with the carrier materials. So the material where the catalyst is actually made of, out of the majority. And this is a material which is porous. And you can see this already here, depending on how porous the catalyst is, you have more accessibility, active sites, more surface area. But if you compare this maybe to a stone versus a sponge, when you have like too much surface area, you end up in where the catalyst gets brittle, so mechanical strength goes down. And of course, if you look into the active material, so the liquid salt phase where the reaction is actually taking place, where SO2 and oxygen migrate into this active phase, get oxidized to the vanadium active material, and SO3 gets released. Of course, you can always increase the activity by adding more vanadium, more promoter salts, or even cesium to reduce the temperature barrier. But this also comes at a cost, because the more you add, the more expensive the catalyst gets. So these are three things that could be regarded separately, but in real life, all three of these topics are closely related. So it's quite difficult to just change something and expect that all the other things will not change. But we, however, figured out that there is a way to make things a bit better with our Quattro catalyst. And basically, you need to figure out how this works in terms of geometry. So when you go down to this image here showing big M&Ms on the left-hand side and small M&Ms on the right-hand side, filled in a jar. This will be our model reactor, so to say. You have big catalyst pieces, you have small catalyst pieces, and then we look at what happens actually during this reaction. So for big pieces, what you have is a low pressure drop, because there's a lot of high porosity. You have a lot of void spaces here. The gas can flow quite freely through this bed. You have a low packing density. You have a low surface area. And this low surface area also relates to that you have a lower conversion, because there's not enough active surface area which helps you to convert SO2 to SO3. Small M&Ms on the other side, they do have a high pressure drop because they have a low bed porosity, they have a high packing density, so the bed is really tightly packed. There's much more pieces in here than in there. But because you have more, you also have a high conversion. The point is, you cannot just mix match and make this to the ideal spot here. If we want to have a catalyst with a very low pressure drop and a high conversion, we need more complex shapes. We need to move away from the standard shapes we knew before. We need to invest time and effort and R&D work into getting more complex shapes. And basically, this is what our Quattro catalyst combines here. We had, when you see an historic overview of what was there before, the ancient pellets with a very high pressure drop but a lower activity. Moving on to the rings here, which were a bit better in pressure drop and activity, and to the old standard, which are the star rings. Our Quattro catalyst, with its improved shape and higher activity, basically managed to get to a significantly higher activity without sacrificing anything on the pressure drop. So we have the same pressure drop for this catalyst geometry, but a significantly increased activity. And we didn't stop with just the activity. So we also optimized our shape in such a way that the catalyst is even stronger. So I can summarize here what this catalyst actually is capable of. We have a 30% higher geometric surface area, which means we also have much higher activity of the catalyst. More importantly, the side crush strength of this catalyst is increased by 50%. So the catalyst is much harder and is less prone to break. And we have a lower attrition. That's quite easy to understand if you compare a ring like a star shape with the edges, which can easily break off. This catalyst has very much rounded shape, which is less prone to get abrasion. So we have 60% lower abrasion of this catalyst. And the loading density is the same. So this is also very important. So you don't need to buy more catalyst in terms of weight to get your reactor filled. It's the same loading density as our star rings are. And more importantly, also no pressure drop increase, which is a huge benefit. So the catalyst combines all the benefits without sacrificing on loading density and pressure drop increase. Moving on. So with this technology, of course, it's always important to show what this technology actually can do. And I will focus here a bit on the improved geometry and what you can do with it. So this improved geometry gives you a higher surface area because you basically have more surface where the reaction can take place. This leads us to two different ways to benefit where the conversion equilibrium, so the maximum achievable conversion of this reaction, can be reached at an earlier stage. So what this means for you, you can either decrease the bed height of the reactor and keep the same conversion because you have more active material present, which means you can reduce your catalyst amount and still have the same active material present for your converter bed. And we've seen that we can decrease the loading of the catalyst by 10 to 20% and still keeping the conversion at the same level as it was before. On the other hand, you can also keep the volume at the same as you have before, exchange your old catalyst with quattro catalyst, and increase the SO2 load, which means the capacity. So you can run at higher SO2 loads and can increase your capacity by 5 to 10%, provided your heat exchangers are capable of removing the energy. But with this, you can increase the capacity significantly without further changes, just exchanging the catalyst shapes from stars or rings to quattro, and have an up to 10% higher capacity with your production. And the higher activity is also very important because for this, the catalyst has decreased ignition operating temperatures. This is related to the fact that you have more active material present at in the active stage at lower temperatures because of the higher surface area, which supports you in startup emission reduction, but also is significantly decreasing your SO2 emissions with this catalyst. And on the last hand side, the improved physical stability gives you less sieving losses, longer catalyst lifetime, less unplanned shutdowns because of pressure drop increases, and overall OPEX reductions due to decreased replenishments with the catalyst. So it's a very versatile catalyst and offers a lot of different benefits for you and your businesses. And today, we just want to focus on the decreased SO2 emissions, which are possible with our quattro catalysts. So before I continue, are there any questions already?
I do not have any questions so far in the Q&A section. If somebody wants to ask a question, please also let me know via chat or Q&A. Or maybe you could also raise your hand if that works, and then you can also do that. But I think for now, Jochen, you can continue.
Perfect. So for the example of reducing emission, especially on startups, I chose an example of our 04116 catalyst, the quattro, for instance, which is a high performance catalyst for minimizing your SO2 emissions. And basically, why is there a need to have a more powerful catalyst? Principle, there's a decreasing SO2 emission limits coming from governments, which is a key driver for converter improvements and also for catalyst improvements. And the historic evolution was basically since the ratification of the Helsinki Protocol in 1985, the limit for the SO2 emission, which we are allowed to emit with our reactors, is decreasing constantly. And what we see, especially in Europe, there might be even newer and stricter limits coming into effect by 2030, which means we need more powerful technologies to decrease SO2 emissions. And here I just give you an example of what was happening over the past 15 to 20 years in Germany. You can see, especially for single absorption plants, but also for double absorption plants, the emission limit that they are allowed to emit significantly decreased over the past 15 years, forcing plant operators and also producers to invest more and further into their reactors. And cesium catalysts here play a crucial role because we need to decrease the temperatures to get higher conversion rates and therefore lower emissions. So we need more powerful low temperature catalysts. And why do we need that? I just give you a brief overview of the oxidation reaction. So the SO2 oxidation is an equilibrium reaction. That means the reaction can move in both ways depending on parameters, and the pathway depends on several factors of the reaction, which is the temperature, gas composition, and partial pressures. And temperature here plays a very important role because when you see this conversion curve here on the right-hand side with the gas composition, the higher the temperature, the lower the conversion of this reaction actually is. That means if we start at very low temperatures with this exothermic reaction, we end up at a higher conversion than if we would start at higher temperatures for the reactor bed. So here's the same. So at 330 degrees, you have a theoretical conversion of 99%, whereas at 1100 degrees, it's just 2.5%. That's also why this then straightforward gas reaction is not possible. And for this, we need to have a catalyst that is designed to be operational at low temperatures to increase the conversion. Something I can show you here. So if we would see a catalyst operating at a normal temperature, let's say 420 degrees, 430 degrees, you would have this exothermic reaction, SO2 getting oxidized to SO3 with the catalyst. And then you end up in the conversion here, which is roughly about 60%, something like this. But if we reduce the temperature of this reaction to 390, 380, for instance, see the same exothermic reaction, temperature is increasing, but it takes much longer for the reaction to reach the equilibrium state. So the state where the reaction backwards to SO2 and oxygen is same likelihood as the forwards reaction to SO3. And we end up in a significantly higher conversion rate for this catalyst. So having a lower inlet temperature is key to minimize your emissions. Yeah. And basically what we did with our 116 catalyst technology to achieve this, we increased our vanadium content and improved our promoter mixture using potassium and cesium. Cesium is a key factor here to reduce the operating state of this catalyst to below 400 degrees centigrade. And we optimized this mix that we ensure the highest activity and conversion at low temperatures. And of course, what we also did is we significantly improved the carrier composition. So we have a higher porosity and pore size distribution, which means we have a higher mass transfer rate at very low SO2 concentrations, which is crucial after intermediate absorption steps where you have very low SO2, high oxygen, and no SO3. And the limit of this reaction is not just the thermodynamics, but also the kinetics, which means the gas is moving into the active phase, reacting to SO3, and then getting carried out of the active phase. So, and just to give you a note about what does it mean to have a different pore size distribution or different carrier material, I was also looking for a nice example for this. And surface area and porosity is quite interesting when you look at volcanic rocks. And I had the pleasure to be in São Miguel at the Azores last year and find some very interesting rocks, which can really nicely visualize what I mean with different surface area and porosity. So when we look at this lava rock 1, you see it has a more rather smooth surface. You see some big pores here, but a very low amount of small pores. Surface area overall is quite low because we only have some of the big pores. And this piece of rock was actually quite heavy and very robust. On the other hand, this is the second rock I found on the same beach. And you can see already like a stark contrast here. So this is very open pored, very rough, has a high porosity, high internal porosity with a lot of pores inside, very high surface area also going into this rock, not just on the surface. And this piece of rock was very light. So it was, I think, maybe a fifth of the weight of this one. So very light material, very porous, and had a very high surface area. both of these are the same origin. They're both a lava. The difference here is how fast the lava was exposed to water and the exterior or gases. So the enclosed gas bubbles either agglomerated and then moved out. So this is why you have these big holes here, or they're solidified immediately and you have this lot of small cavities of the small gas bubbles. Good. With this example, of course, how can we translate this to our catalyst? And this we need to look at our diatomaceous earth, so the carrier material, which is important for our catalyst properties. And I have now 3 examples for you of diatomaceous earth as a natural product. So these are actually fossilized shells of silica algae in various shapes. So these come from prehistoric times and getting mined. And they can have very different shapes. And the shapes I show you here is like disc-like shapes, we have rod-like shapes, and we have cylindric shapes. And depending on how you combine these shapes together, you can have a significant impact on key catalyst properties, which is very interesting. So the way you combine it, you can increase your strength. You can change your operating temperature. You can make it higher or lower. You can change the surface area, which is quite obvious here because you have a lot of different porosities. And you can change the activity, which is closely related to surface area and porosity. And if you combine these keysigures smart, you will have a catalyst that has a high activity at low SO2 concentrations and low temperatures. And this is what our 04116 looks like. And when we now compare this to old cesium-based catalysts, which were designed to be very sturdy and be able to also operate on the first bed at high SO2 and high temperatures, the carrier composition here with the old 115 was developed to withstand high temperatures, first pass, high SO2, high SO3 concentration, and the need here to have a highly porous and active catalyst is not so high because the conversion limit is actually the equilibrium, so the temperature range, not how much gas we can get into the active surface and out of it. So having an increase in porosity has no benefit. On the other side, the 116 Quattro, we designed it for the applications after the intermediate absorption step, where SO2 is low. We have very low SO3 to none, and we have a high oxygen ratio. And the conversion here is limited by the rate of diffusion rate of the reactants into the active mass. So the structure of this catalyst has to be more favorable for internal mass transfer. So we need to get more, it need to be easier to get the SO2 and oxygen into the surface and out of the SO3 out of the surface as fast as possible. And with our recipe and also with the benefit of Quattro, we observed that we have a synergistic effect of those two, which means that the mass transfer and also the activity of the catalyst is significantly higher than you would just look at the two things separately. And this is something you can see here already. It's a lot of numbers, but when you compare our standard starring catalyst with the high performance Quattro catalyst for the 115, so for the standard cesium promoted catalyst, you already see with this higher surface area, you get a decrease in your ignition temperature for the 115 by 10 degrees down to 330 from 340. And the operating range decreasing to 375 up to 630. So this is a significant decrease in the operating range. Same here is true for the 116 Quattro, but a much more extended state. So we can even decrease the ignition temperature down to 320 degrees centigrade and further decrease the operating range to 365 degrees centigrade, which means the catalyst is active and does actively convert SO2 to SO3 at this low temperature range. And in summary, like the superior carrier material composition lead to this higher activity. And we really optimize this catalyst for low temperature applications, which you can see here, it's very low. And the ignition and the operating temperatures of the Quattro catalyst and this versus the starrings show that there's a synergistic effect. So you see here from starring to starring, you just have a 10 degrees reduction, whereas when you go from starring to Quattro, you get 15 degrees. And this support is basically just by the synergistic effect of having a significantly improved geometry and a better better composition of the catalyst. Good. And how does this pan out in terms of kinetic rate? So we can also see for the Quattro catalyst, at lower temperatures we see a higher activity versus the 115 at very low temperatures between 20 and 40%. So the catalyst is more active at lower, significantly more active at much lower temperatures than the standard cesium catalyst would be. At higher temperatures, this is leveled out a bit, so we're just down to 15 to 20%. This is because of thermodynamic contributions, making it a bit more less pronounced. But overall, we can say we have up to 40% improved kinetic rate, which means this is maximizing the conversion at low temperatures. Good. Before I go to the example, are any questions about the 116 Quattro?
We have received one question, but actually, Jochen,
Perfect.
you answered it already.
Okay.
So it was about the strike temperature, but you referred to that already. So consider this one done. And then I just received another one. What was the gas composition for the kinetic data on slide 23?
Oh, I have to look that up. Usually we do this at a composition of, I think, 7% SO2 and 10% oxygen, something like this.
Okay, thank you so much. This is it for now.
Okay, thank you. Good. Then let's move into the example where we're showing the emission reduction upon plant startup. So basically, I just talk a bit about the details. This is a double absorption plant with 4 beds, and it has an intermediate absorption tower after bed 2, so DA22 unit. And some details, it's a zinc smelter in Europe. We have a rougher daily capacity of 1,080 tons per day. Average gas composition is around 130,000 norm cubes. Bit below 8% SO2, 10% oxygen. Target conversion of this reactor is 99.9. And the important thing here, especially in this part of Europe, they do have an annual emission limit contingent. So they have an amount of SO2 in kilograms they are allowed to emit. If they exceed this, they get into trouble. And as we all know, startups produce the most amount of SO2, so that really the goal is to reduce the emissions upon startup after shutdowns, which are hot or cold. And during this project, we decided to implement a cesium layer in the third bed to decrease the emissions upon startup, to really go down with the emissions. And we chose to use 116 Quattro as the best, because it has the best performance with the lowest catalyst volume to achieve this goal. Just showing you here how this reactor bed was actually looking like. So we had starring catalyst in the first 2 passes, and we still had the old ring catalyst in passes 3 and 4. So they were quite old still. And when we see here some of our performance measurements that we did in Jan 2022, could see that basically we achieved a conversion of 99.89%. And we could see that performance in bed 3 was not so good as well as bed 1, but this is basically because of the age and should be exchanged any case. So we recommended an exchange of bed 1 and 3 to regain the performance of the unit and to go with the ignition layer in bed 3. And this is what the plant looked like afterwards. So what we did, we put in a fresh layer of fresh set of catalyst in bed 1, and we also replaced the bed 3 entirely. The majority of the bed, 70%, is still 111 starring. Why didn't we go for Quattro here as well? Is because we really wanted to see just the benefit of the 116 Quattro, and not having it overshadowed by the other Quattro catalyst. And the remainder, bed 2 and 4, remained the same. And after the change out and after almost a year in operation, we did some performance tests again. And what we could see here already, the exchange had a significant impact here. The conversion overall increased to 99.93. and the conversion bed-free was 96.91. So we had a significantly improved cumulative conversion, but also the separate conversion bed-free was very, very high, which is good. But it gets better when we look at the startup behavior of this reactor. And here I have an historic startup behavior before the implementation of the Quattro catalyst, and what you could see here. So the blue dots is the gas flow, and the red line are the emissions in ppm. And you can see after the start of the gas flow, you have a small dip, then it's a bit lower, and then you see this huge increase peak in emissions, which then levels down to around 120 ppm after the startup peak of around 180 minutes. If you sum up of these 3 hours, you roughly end in an emission of 94.7 kilograms of SO2 emitted during the startup. We then did the same exercise a year later, and there you can see a very different behavior. Right at the startup, you can see that we have start of the gas. You can see we have a high emission peak, which goes up to 12,000 ppm. This is basically because bed 1 was still super cold, which then immediately decreases down to 25 ppm and stayed like at this level for a very long time until it's leveling at around 85 ppm. So we could see that directly after the ignition layer here in bed 3 kicked in, we could catch the emissions down to a level where it was significantly less than before. To sum this up, we only had an emission of 17.08 kilograms in these 180 minutes, so which is a significantly decrease in the emissions. So when we compare those two different startup behaviors before and after the exchange, we can see that the emission reduction over these two periods of 180 minutes was decreased by 82%. The reduction relatively was 77.6 kilograms of SO2 could be avoided of being emitted to the atmosphere, which is a great benefit and really helps the customer to really get down to the emission limits. Furthermore, what we could see here is that this third bed displays a significantly increased activity at 350-degree inlet temperature. So when the plant was started up, we could already see significant activity in bed 3, which was not observed in all the startups before. So also the contribution at this very low temperature made it possible that the reduction in SO2 emissions was so significant. Good. Let's sum it up. So what we could do here in this exercise was we could successfully implement our 116 Quattro catalyst as ignition layer after intermediate absorption. We could increase the conversion up to 99.3%, and the most important thing is that we can decrease the startups emissions by up to 82%. For the client, he's very satisfied with this result because it's a major contribution to tackle his emission targets. One thing I have to say here, this emission reduction is of course also only possible if you have a good startup procedures and you stick to them as best as possible, because if you start the gas when everything is below ignition temperature, you will not get to this emission reduction. So you also need to have your operation excellence really on top to get this down to this low levels. Good. And the part is, I mentioned at the very beginning of my talk that we didn't stop with the Quattro, and here's some interesting outlook for you to see how we intend to further decrease in startup emissions using our new X3D technology. Basically, this catalyst is a cutting-edge shape based on 3D printing technologies. What you can see here when you compare our 116 Quattro with the X3D technology, we have an even higher surface area. We have a significantly lower pressure drop, which can be very beneficial for increasing your operation runs. The ignition temperature is even 10 degrees lower, and the operating temperature drops down even further. So this is even even better to decrease startup emissions or have this catalyst as ignition layers after intermediate absorptions, towers, or even at the first bed. And I wouldn't just tell it because we have this nice R&D activity. Basically, this catalyst is reality. We are building a new production plant which will start up in 2026 and will deliver this catalyst in large commercial scales. And with this, I'm at the end of my talk. Thank you all for your attention. And are there further questions?
Thank you very much, Jochen, for guiding us through. Please keep the questions coming if you have any. And yes, I do also have one more for you. How does the quattro catalyst shape fare with particulate matter impurities in the gas? Does it block easily and can it be screened?
So the particulates, basically the catalyst fares a similar way as any other catalyst fares. They will attach to the surface, but you can screen it in the same way you screen standard catalyst. There is no difference because all of the chemistry behind this catalyst is identical. So, and it's even harder, so it's less prone to break and abrase during the screening process. So it's much easier to screen.
Great, thank you. Oh, and there was a follow-up question on this one. Is this a risk for the X3D shape?
Not that we know of. So we haven't screened it yet. We have references which are now running for more than 6 years. The clients are so happy that they don't want to open the reactor beds because the pressure drop is so low and is not moving since these 6 years in operation that they don't want to test screen it or so forth. I have spoken to several screening companies and they're actually looking forward to seeing this catalyst because they think it will be handled much better and can also be better screened than the current catalysts. But that's something we need to find out in the future.
Good, excellent. So thank you for this interesting presentation, Jochen. Can you comment on the maximum CO load which is allowed for your catalyst? CO is often encountered for metallurgical off-gases.
Mm-hmm. So basically, we have not encountered any issues with CO in the catalyst. So there should be the CO should be not a poison per se or like a counter for this reaction because the catalyst doesn't have the active sites to connect to CO. You can see a decrease in activity, which is non-permanent. So it's not a poisoning, it's just a little bit of deactivation. You also have issues with the reduced activity with the what's it called? With the thermal capacity, same as CO2. But I don't think we have any limits for this, and we didn't see any significant drawbacks in having CO in the gas phase, not to my knowledge.
Good. Thank you so much. So there was one question in the chat, but it disappeared. Raising question in the chat is, of course, possible as well. I think it was on the thermal stability of the catalyst, Jochen. Can you refer to that?
I can refer, but the question is thermal stability. But this is basically stability of the catalyst is basically determined by the choice of the carrier material. And we developed our catalyst like for the first pass for being able to withstand temperatures of 630 degrees under like normal conditions and surviving peaks up to 650 degrees. This is usually also what your steel can last. So this is why we optimize this temperature limit for this for our catalyst. For beds in like beds 2, 3, 4, where the temperature increase is not so high, we focused on lower on activity and performance increase, And that's why our like 111, 116 catalysts, they have a lower thermal stability up to 600, 630 for spikes. Because usually you don't see 630 degrees in your second bed. You shouldn't actually.
All right. I have twice a thank you to you for this interesting presentation and discussion. So there is so far no question open. And I think then we can also close that. Let me, oh, there's one coming up. Very good, there's one coming up. Is there any difference in arsenic or other heavy metal poisoning if you compare rings, star rings, quattro shapes, pellets, XVD catalyst? I think of the example application of the catalyst in metallurgy you showed.
No. Actually, no, because the poisons attack each and every catalyst the same way, and that's a bit difficult. So the impacts will be the same. Of course, if you have higher activity, you will see deactivation through poisoning later, which makes it actually a bit more difficult to counteract because the agglomeration of poisons is higher before you really see the impact, and this can already be too late and you need to change. But since we have this higher stability of the catalyst, I would expect that this will not negatively impact any campaigns. Will work the same way, but you need to keep your poisons in check for all catalyst types actually, because you can have sudden pressure drop increases because of catalyst deterioration, or you can have beds deactivating because of arsenics for each and every catalyst. This is like a global issue. This is not just for our catalysts.
All right. Good. So maybe something else comes in, but in the meantime, let me please repeat what I said in the beginning. We will share the presentation or the video with you in the upcoming days. We will also make sure to, with that email, send you the contact of Jochen and Sol. So if you have any follow-up questions, you can, of course, always raise the questions to us and we will get back to you. So as there is no question incoming, I would like to thank all of you for joining our webinar today. Thank you so much, Jochen, for your expertise and input. I think we will see each other soon, maybe at the conference at the end of the month in South Africa.
Exactly. Stay tuned for that. I have very much more different examples to show you there during my presentation at the conference, but also at our workshop, which we'll be giving on Monday.
Excellent. Thank you, Jochen. Thank you, everybody joining in. Have a wonderful day and see you soon. Goodbye.